Ladies and gentlemen, once again, I have the pleasure of welcoming you to the Congressional Auditorium here in Washington, D.C. for what is already the third edition of the National Lab Research Slam. You remember how it works? 17 early career researchers, each of them representing one of the 17 national labs of the DOE, the US Department of Energy, will share with you the highlights of their research in just 3 minutes and a single static slide here on the screen. And this year again, I will have the honor of introducing them to you, and I had the privilege of training them on structure, slides, and delivery. Right? So, between you and me, I would not want to be one of the judges here. Because if I did my job well in the previous few weeks, and if the finalists do their jobs well today on stage, it's going to be mission impossible to pick a winner, right? The event that you have today is going to be a showcase of what the national labs are doing for this country in terms of energy security, national security, scientific discovery, and advanced materials. And obviously, it's going to be only a small sample. The national labs do a lot more than that. But yes, I was telling you about Mission Impossible to pick a winner. Do you realize that the jury this afternoon will have to pick a winner in each of the 4 categories? So let me introduce the judges to you. In the middle, the senior advisor at the US Department of Commerce, also a former director of the Office of Science for the US Department of Energy, Dr. Chris Fall. On his right, the director of the Office of Strategy and Technology Roadmaps, also Deputy Chief AI Officer for the US Department of Energy, Helena Fu. On their left, the director of the Bipartisan Commission on Biodefense at the Atlantic Council, Dr. Asha George. Seated at the far right is a retired NASA astronaut, currently president and CEO of Tierra Luna Engineering, Jose Hernandez. And seated far left is the Senior Director of Government Affairs, Special Competitive Studies Project, Jenny Keefe Singer. Those of you who have been with us since the beginning of this adventure may have noticed that this time the 4 categories are particularly well balanced, the best they can be given 17 contestants. Sure, scientific discovery is still the largest group, reducing ever so slightly the odds of winning. But hey, it's unavoidable, and it's far less an imbalance as we have had in the past. Plus, we also have the People's Choice, awarded by the audience, you here in the Congressional Auditorium, and you out there watching this event remotely. I will share with you a QR code later on to do that, but for all of the 5 awards, the criteria are structure, slide, delivery. Structure: is the talk making you care? Is it clarifying the researcher's contribution? Is it conveying a message? Slide: does it illustrate this message visually, or does it, heaven forbid, distract from what the speaker is saying? And delivery: do the words, the voice, the body language contribute to engaging the audience. In a nutshell, do you get the point? Clearly, effortlessly, enjoyably. Well, you tell us at the end with a QR code I'm going to share in due time. In the meantime, how about you use your smartphones to take pictures and to share them widely on social media using these hashtags? Like a bad teacher, I'm going to give you 5 seconds to write them down before I move to the next slide and introduce the first category of 3-minute talks for this afternoon, energy security. Researchers at national labs, including the first 4 finalists for this afternoon, pursue technological solutions to provide abundant sources of energy and to support energy infrastructures. You know what? How about a word of encouragement from their congressional representatives?
Hi, this is Congressman Mike Simpson, proudly representing Idaho's 2nd Congressional District, wishing the best of luck this evening to Dr. Karen D'Souza from the Idaho National Laboratory. Idaho is cheering you on.
Hi, this is Senator Dave McCormick, proudly representing the Commonwealth of Pennsylvania. I'd like to congratulate Dr. Will Straw from the National Energy Technology Laboratory on his selection as a National Lab Research SLAM finalist.
Hi everyone, it's Congresswoman Brittany Pedersen, proudly representing Colorado's 7th Congressional District, which is home to the National Laboratory of the Rockies. I'll be cheering on the National Laboratory of the Rockies' own Kalen Rasmussen as he competes in the 3rd National Lab Research Slam. Good luck, Dr. Rasmussen.
Hi everyone, Congressman Chuck Fleischman. Congratulations to everyone for the National Slam competition, especially from the Oak Ridge National Laboratory, Dr. Brian Conry. I wish you well.
All right. If you have read Samuel Taylor Coleridge in English, or perhaps Charles Baudelaire in French, then you might associate the albatross, especially one around your neck, with a psychological burden. But if I tell you that our first speaker this afternoon was nicknamed the albatross by her high school swimming team, then you realize that is quite a compliment. In the 7th grade, she could beat swimmers from the 12th grade. You imagine the humiliation for the 12th graders? Oh my goodness. Ladies and gentlemen, from Idaho National Laboratory, Dr. Karen D'Souza.
What if the satellites that we rely on for the internet suddenly stopped working? What if your phone, your laptop, suddenly became 4 times more expensive? And what is common among these devices? They rely on critical metals. Metals we don't produce here in the US, like samarium. It's the most vulnerable critical metal in the US. We import 100% of it, making our supply chain fragile. So what is the challenge? Chemically, these metals behave like twins. Same size, same charge, same preference for binding. And they're tangled in the same minerals. We don't fully understand how to separate them. Is it the temperature, charge, acidity? Without that knowledge, we're stuck guessing. And there's another problem. Traditional methods of separation rely on harsh, toxic chemicals, the kind dying banned in the US because they pollute our environment. So we need a solution that's simple, safe, yet still effective. And that's where vinegar comes in. Yes, vinegar. In the lab, my group lines up a row of critical metals, like samarium, like dysprosium, add a few drops of vinegar, apply an electric current, and just like that, the metals begin to drift apart. Vinegar shocks them into revealing their secrets. But don't be fooled. Just one small change, like tweaking acidity, and the separation fails. And figuring that out, it's so slow, it's so expensive, and it takes months of trial and error. And that's why I turned to AI as the solution. Not to replace the science, but to scale it. Using experimental data from the lab, I tag on the physics of the metals and train machine learning models to predict how small changes in the molecular structure or the acidity can actually control how these ions behave. And here's the real power. I'm not just testing these separations anymore. Using AI, I'm designing them. And the impact of using AI? It's speed, scale, and automation at a level unimaginable in seconds compared to traditional experimentation. And more importantly, the US can rely on a resilient domestic supply of critical metals that power our next generation of technology. So yes, vinegar. It sits quietly in our kitchen pantry. But at Idaho National Lab, vinegar paired with AI helps us rethink critical metal separations, because this isn't just about chemistry. It's about securing the metals that power our technology, from the smartphones in our pockets to the satellites up above.
Again, thank you, Karen. Now, you in the room, did you hear that? The next time you have guests for dinner, you ask them, would you like some more critical metal separator on your salad? Right? Okay, you know it. Everybody knows it. Researchers are curious about many things. Our next speaker is a bird-watching enthusiast. In the Pittsburgh area, he can identify 80 to 90% of the species by call. How much is that in absolute terms, you ask? Well, Pittsburgh has tens of resident species, increasing to possibly hundreds of species in the summer by migration. His favorite, for its call, is the white-breasted nuthatch. And no, I am not going to try and imitate it for you this afternoon. Ladies and gentlemen, from the National Energy Technology Laboratory, Dr. William Strahl.
You're grocery shopping on a tight budget, balancing health and cost. Do you choose organic blueberries or potato chips? Likely, you'd choose something in between, something that is healthy enough, but not too expensive, a trade-off. This exact dilemma shows up in a completely different context, deciding which oil and gas wells to plug. Across the United States, there are millions of wells reaching the ends of their productive lives. These wells reduce oil and gas production by providing underground escape routes. They also block new hydrocarbon development, where in many cases, old existing wells must be plugged to drill new ones. Eventually, they must all be decommissioned, but it's incredibly expensive. On average, it costs $76,000 to retire just one well. But grouping nearby wells with similar characteristics can unlock huge cost savings. State agencies decide which wells to plug using taxpayer dollars, and they have to make trade-offs, like grocery shoppers on tight budgets. But instead of balancing health and cost, they are balancing impact. Which wells matter most for their state to plug? Like older wells, wells with block development, their priorities can be anything, and efficiency or cost of plugging. Typically, they can't find the best trade-off between impact and efficiency. Why? Because there are millions of possible options. Evaluating them all isn't practical. It would take years. So, they miss out on the best outcome. This is why we harnessed machine learning and mathematical optimization at NETL to develop Primo, a fully customizable decision support tool that can evaluate millions of possible options in seconds. It quantifies these trade-offs, and it allows decision makers to make transparent and defensible selections that are in the best public interest. Primo uses a simple three-step workflow. First, users upload their data. Second, users select their priorities for impact and efficiency. And third, Primo tells users which specific wells to choose to get the best of both worlds. And to make this easy, we've created a user-friendly website that anyone can use. So how effective is Primo? In a case study comparing Primo with a typical state agency approach, Primo recommended plugging projects that were 23% more impactful and 21% more efficient. Now, these trade-offs, they're unavoidable. But with Primo, we don't miss out. It can turn state agencies from grocery shoppers struggling to find the best trade-off into grocery shoppers that know exactly how to get the most health and value for their budget, and that is the power of Primo.
Thank you, William. So those of us who don't plug wells, we should ask him to develop a version for grocery shopping, right? You know, health benefits versus how expensive it is. Now, if you thought a lab can be a dangerous place, try conducting research in the field. Our next speaker for his PhD studied the biology and geochemistry of hot springs, mostly through field work in Yellowstone National Park. So besides having herds of bisons checking him out, which can be intimidating enough, he was chased once by an elk and once by a grizzly bear. Comparatively, I think I had it easy. The only species to ever chase me during my PhD was my PhD advisor, really. Ladies and gentlemen, from the National Laboratory of the Rockies, Dr. Kalen Rasmussen.
How many of you use a device that requires a battery every day? Batteries power the modern world, but they depend on critical metals like cobalt, lithium, and nickel to harness the energy that drives our daily lives. To build batteries in the US, we must import these rare and expensive metals from other countries, including geopolitical rivals. And we have to keep buying more because we go through roughly 250,000 tons of batteries every year. For context, it would take 7,000 fully loaded semi-trucks to haul away just 1 year's worth of spent batteries. And unfortunately, those crusty and corroded batteries often end up in landfills, removing critical metals from our supply and making it harder to build batteries in the US. Current battery recycling is either very inefficient or involves harsh chemicals that generate a lot of toxic waste. At NLR, we're using a different approach to recover these critical metals, and the key is a teeny tiny hero, smaller than a single particle of dust. Meet ferrooxidans, a microbe found in toxic mine waste who enjoys a cold plunge in an acid bath and eats CO2 for breakfast. We use ferrooxidans in a process called bioleaching, where the microbes create an environment that dissolves the battery metals, allowing them to be purified and remanufactured into sparkly new batteries that power your next phone, tablet, or smartwatch. But the big problem is the dissolved metals are highly toxic, even to ferrooxidants, killing them and halting the recovery process. My job is to turn our microbial hero into a metal-resistant superhero. I put ferrooxidants on a specific training regimen to increase their resistance to toxic metals. By applying selective pressure and accelerating transformative change, I increased their resistance to cobalt, lithium, and nickel by over 70%. That's a massive shift in toxic metal resistance that renders my new, evolved version of ferrooxidants capable of thriving in the harsh battery environment, and increases metal recovery by 40%. My supercharged version of ferrooxidants can now recover critical metals that are already in the US, enabling energy security and removing batteries from landfills without harsh chemicals. While batteries power the modern world, microbes allow us to power the US independently.
Thank you, Kalen. So, in the end, which was the most fearsome species? Grizzly bears or ferrooxidants? Well, our next speaker does not need to be chased by an elk or a grizzly bear in order to hit the trail, because he is an avid hiker. Located at Oak Ridge, is not that far from Great Smoky Mountains National Park, where he has hiked most of the trails. Over the last 2 years, he's probably been hiking 400 miles total, which is a bit like coming to Capitol Hill on foot from Oak Ridge. Ladies and gentlemen, from Oak Ridge National Laboratory, Dr. Brian Conry.
What do a hospital, a data center, and a rural community all have in common? They all need steady power. And as our energy demands grow, the challenge is not just in making more electricity. It's delivering reliable power where and when it's needed. But that's why it's delivering reliable power where and when it's needed. That's why my research is focused on, it's about delivering reliable power where and when it's needed. Some places, large grids do need large-scale power, but others, like military outposts, universities, and even disaster relief efforts, need smaller local systems. That's why my research is focused on TRISO, What do a hospital, a data center, and a rural community all have in common? They all need reliable power. But the future Large grids need large-scale power. But, for instance, military outposts, universities, and even disaster relief efforts need smaller local systems that operate around the clock. So the real question is, if we want nuclear to satisfy more of these roles, wouldn't it help to have a fuel that is extremely robust, handles very well at high temperature, and enables reactor designers to focus less on active safety systems and more on efficient power generation? That's why my research is focused on TRISO fuel, which is a fuel that satisfies all of these boxes. Instead of one large pellet, TRISO is made of thousands of microscopic particles, each one the size of a poppy seed, surrounded by multiple protective layers, sort of like tiny, self-contained pressure vessels. In my research, I study TRISO at the particle scale to build confidence in how it performs. One of the tools I use is X-ray computed tomography to look inside of these particles in 3D and identify any defects without destroying the fuel, just like a CT scan at the doctor's office. I can then correlate these tiny flaws to the performance of the fuel under reactor-relevant temperature and irradiation. And those results are critical, because if we want this technology out in the real world, we need to show what works and also what doesn't work. And that's really the bridge between a promising idea and a deployable technology. And we're getting close to crossing that bridge, because multiple reactor units here in the US using TRISO fuel are scheduled to be operating by 2030, with demonstration efforts as soon as this summer. These projects are led by companies like BWXT, Kairos Power, and X Energy, and will represent some of the first real tests of whether TRISO can move from cool concept to reliable energy infrastructure. So when we talk about the future of nuclear, it's not just about reactors. It's about building systems that deliver reliable and resilient power where it's needed most. And whether that is a hospital, a data center, or a rural community, TRISO fuel is a key piece in making that future a reality.
You know, I was at a hotel recently and I had a leak in my bathroom. So I went to complain at the reception about that. And they started apologizing profusely about it. And I stopped them and I said, look, I don't judge you by whether there is a problem or not. I judge you by how you handle a problem once the problem appears. And I don't know about you, but I think that our last speaker demonstrated that beautifully. Yes. This concludes the first category, energy security. Now on to another form of security, kind of an obvious one, national security. National lab researchers, including the following 4 finalists, ensure the safety, security, and reliability of this country's nuclear deterrent and address emerging threats to geopolitical stability. Once again, a word of encouragement.
I'm Congresswoman Teresa Ledger Fernandez, representing the beautiful and beautifully diverse 3rd Congressional District, including the Los Alamos National Lab. And I'm here to introduce Dr. Marina Mancuso, who is part of the lab and part of the lab's Information Systems and Modeling Group. Her research focuses on using artificial intelligence to better understand the body's immune system and identify unknown pathogens. When we know what we're up against, we have a better chance to keep us safe and to keep our communities healthy. To Dr. Mancuso, thank you for the work you do. Helping us understand these complex systems called the human body will help keep us safe, help keep us healthy, and does so much for not just New Mexico, but for the world. Muchísimas gracias and good luck.
Hello, I'm Kim Budell, Director of Lawrence Livermore National Lab. I want to congratulate Keegan Orr on being selected as a finalist in the 2026 National Lab Research Slam and wish him the very best with his presentation. I'm very much looking forward to hearing more about his work to understand and improve materials that can survive the extreme heat and plasma conditions of hypersonic flight. It's a wonderful example of the kind of ambitious, mission-driven science we do at Livermore in service to the nation.
Hello, this is Congressman Dan Newhouse, proudly representing Washington's 4th District, home to the Pacific Northwest National Laboratory. I want to wish the best of luck this evening to PNNL's own Dr. Peter Lawler as he competes in the 3rd National Lab Research Slam. Good luck, Dr. Lawler.
Hello, ladies and gentlemen. I'm Joe Wilson, Member of Congress, grateful to represent the people of the 2nd District of South Carolina. The Savannah River National Laboratory is a critical contributor to the national security of peace through strength for the United States and an appreciated community partner to South Carolina and Georgia. Today, I am especially grateful to recognize Dr. Austin Abbott as a researcher with the Savannah River National Laboratory. Dr. Abbott was selected as the winner of the competition to represent the lab, contending against the other national lab nominees from around the country. As the only member of Congress who has ever had the opportunity to work at the Savannah River site myself, I know of its dedicated personnel. Congratulations, Austin. We wish you well. Best wishes for everyone at the laboratory. Thank you very much.
When you have a researcher's problem-solving skills, you can apply that to pretty much anything, right? Our next speaker is a board game enthusiast. She's been playing, I believe, 50 different games with friends and husband over the last year alone. Frankly, I don't think I've played that many games myself over the last 50 years. She plays most Thursday nights in, guess what, a bar in Santa Fe called Keeping Together. I was impressed when she told me that she owns 60 different games, but apparently a friend of hers owns 300. Ladies and gentlemen, from Los Alamos National Laboratory, Dr. Marina Mancuso.
Show of hands. Who here has stumped their doctor by being sick with super general symptoms? I've experienced this too. The problem is that current diagnostic tests are pathogen specific. Each test looks for a specific microbe, so you only get information through the process of elimination. This isn't just an inconvenience. It also has 2 dire consequences. First, misdiagnosis increases our risk of antimicrobial resistance when the wrong treatment is used to fight an infection. By 2050, this could cause over 10 million deaths each year and cost a total of $100 trillion worldwide. Second, this issue critically impacts our national security. What do we do when we're faced with an unknown pathogen with no available diagnostic test? We need a way to rapidly detect and accurately classify novel pathogen types to protect our country from emerging biological threats. But there's a better way to diagnose infection. Instead of having multiple tests look for a specific microbe, we could take a personalized approach by analyzing signals from our body's innate immune system. This system is our body's first line of defense against invading microbes, activates within minutes to hours upon infection, and enables pathogen classification from just one test. The innate immune system has hundreds of protein signaling pathways and a network too complex to decode manually. But at Los Alamos, we're using AI to tackle this challenge that's never been done before. With AI, I could classify pathogens as viral, bacterial, or fungal from a single test, reducing the time for medics to deliver life-saving treatments. To build my models, I'm using genetic data generated by scientists in our chemistry division. After 24 hours, they measured the strength of proteins that elicit inflammatory response. My AI models detect patterns in these biological signals to enable pathogen classification. Specifically, I designed a sampling and data curation procedure to ensure predictions remain accurate on new data the model has yet to see. Just 24 hours post-infection exposure, the model showed 93% correct classification accuracy. This gives a sense for how much my models can be trusted and provides a tool for rapid pathogen detection. With AI, we can reduce our risk of misdiagnosis, causing antimicrobial resistance, and protect our country from emerging biological threats by intelligently decoding our innate immune system. So the next time you go to the doctor, they'll know why you're sick.
Thank you, Marina. I sure wish my family physician were in the room right now for this presentation. Now, every finalist this afternoon is a world-class researcher, but only one of them is a world-class yo-yoer. World-class as in top 50 worldwide. Let me say no more, just search him on YouTube, and not now, after the event. You're going to see it's insane. Now, he was also great with a pogo stick, jumping 8 feet in the air until he broke his leg. So as he comes on stage in just a few seconds, I am going to refrain from saying break a leg, but I wish him every success all the same. Ladies and gentlemen, from Lawrence Livermore National Lab, Dr. Keegan Orr.
If you want to deliver a pizza anywhere in the world in under 20 minutes, that pizza's got to go fast. How fast? Really fast. Probably 5, 6, 7 times the speed of sound. If something goes that fast, that's called hypersonic. But you might wonder, haven't we gone that fast before? Like just last week when a capsule carrying astronauts re-entered the Earth's atmosphere? And we have. But that's when they go way up into space and come way back down, briefly punching through the atmosphere. And while that's a fast way to deliver a pizza, everybody knows where that pizza's going. And if you were really hungry, you could intercept that pizza. Instead, our pizza will go into space just for a moment, fall back down into the atmosphere at hypersonic speed, but instead of punching through the atmosphere, it will stay there, maintaining that speed, cruising around the world. This will allow our pizza to travel undetected and make unpredictable maneuvers so it can't be intercepted. Now, when you do that, the surface of the vehicle will be subjected to a lot of really extreme conditions, more extreme than those re-entry capsules. You'll have high heating due to friction. You'll have plasmas forming from shock waves. And if we don't want to deliver a burnt pizza, we're going to need some new materials, and that will require some new science. So, to develop those new materials, we have built a hypersonic wind tunnel at Lawrence Livermore National Laboratory. Material scientists and engineers can place Oreo-sized samples of their new materials into our wind tunnel. Then, using powerful lasers, we'll heat those samples up to temperatures relevant to our pizza delivery vehicle. Then we'll use additional lasers to measure how those materials respond. Because when you heat something up to these crazy high temperatures and you flow gases over it that quickly, it'll just start to fall apart. It may ablate, it can vaporize. You'll have all kinds of chemistry occurring and gases forming on this sample's surface. And these material scientists and engineers, they would really like to know exactly how fast, where, and what is coming off of that sample. That information will help them invent better materials. So that's where I come in, with an additional laser. With the right color of laser, those gases will absorb some of that light, and then they'll re-emit it, fluorescing the light at a different color. Then I use high-speed cameras, and I capture that re-emitted light, and that gives me real-time information about exactly where, how fast, and what came off of that sample. And so, with our wind tunnel and our lasers, we're going to help materials scientists and engineers create new materials so that they can build a vehicle capable of delivering a pizza anywhere in the world in under 20 minutes.
Thank you, Keegan. Did you guys get that pizzas were actually a metaphor for something else that the military might want to be delivering? Oh, good, because the first time I heard that talk, I took it way too literally. I had my hopes up because I love pizza. Now, as you probably know, many scientists are skilled musicians, and we have 5 among the 17 finalists this afternoon, but how many scientists, musicians, can claim that they played at the Super Bowl halftime? Our next speaker did, together with Coldplay, Bruno Mars, and Beyoncé. Remember that one? Must have been in February 2016. At the time, he was an undergrad at UC Berkeley and was playing glockenspiel in the Cal Marching Band, which is almost as famous or as infamous as Bad Bunny. Ladies and gentlemen, from Pacific Northwest National Lab, Dr. Peter Laller.
The video game enthusiasts in the audience might have heard of the action-adventure title Grand Theft Auto 5. But did you know it was used to help train self-driving cars? It turns out simulated worlds are the perfect testing ground for machine learning. They're rich, unpredictable, and endlessly customizable. But there's a problem. What if your self-driving car encounters something in the real world that would never appear in a video game? You don't want to run a stop sign just because the paint is worn, the sign's tilted, or it's foggy outside. These same challenges exist when detecting dangerous nuclear materials. At PNNL, we're building smarter machine learning algorithms to identify radioactive threats quickly and reliably, helping reduce costs and safeguard national security. We often use simulations to train our models. But simulations are just that, approximations. In the field, backgrounds fluctuate, detectors age, and shielding distort signals in ways simulations don't fully capture. So how can we be sure that a model trained on simulations will still work in the real world, where sensors are noisy and conditions are never perfect? To bridge that gap, I use a technique called domain adaptation. It's a way to transfer what a model learns in one domain, like simulations, to a new, related domain, like real-world measurements. I start by training a model on synthetic radiation data, cheap and safe to generate, and then fine-tune it on a small number of real-world examples. It's just like how a pilot spends hundreds of hours in a flight simulator before they ever fly a real plane, first mastering the fundamentals in simulation, then tuning to the feel of an actual aircraft. And the results are exciting. After domain adaptation, my models become much more reliable on real-world data, even when that data is noisy, distorted, or unfamiliar. Furthermore, when I look under the hood, I can see that my models are picking up on the same physical signatures that a human expert would use. In other words, I'm not just building AI that works, I'm building AI we can trust. By translating what my models learn from simulations to the real world, I develop radiation detection systems that are both efficient to train and reliable in the field. Fewer false alarms and missed threats means faster decisions and tighter screening. In this critical domain where real-world data is difficult to acquire, this capability is essential for deploying secure and trustworthy AI, the kind that works just as well on the streets of DC as it does on the streets of Grand Theft Auto 5.
Thank you, Peter. And do you know what is scheduled to be released in November? Grand Theft Auto 6. Oh yes, I can't wait. Now, our next speaker may not have played the Super Bowl halftime, but hey, he plays the piano, not good for a marching band. He likes to play ragtime. You know what that is? Ta-ta-ta-ta, ta-ta-ta-ta. All together. Ta-ta-ta-ta-ta-tum, ta-dum-tum. If you recognize that, then I did a better job than trying to imitate the white-breasted nuthatch. Right? Ladies and gentlemen, from Savannah River National Lab, Dr. Austin Abbott.
Think about how you feel during allergy season. Pollen in the air maybe makes your eyes watery and itchy, makes you sneeze, or gives you a sore throat. But imagine instead of pollen, you inhaled radioactive dust. That would make for a pretty bad day. And while it is unlikely that there's nuclear material floating in the air around us, it isn't impossible. There are facilities in the United States that processed radioactive material, mostly during the World War II and Cold War eras, and are no longer operational. Many of these sites are currently undergoing deactivation and decommissioning processes, which help to minimize the cost of upkeep. Unfortunately, as a result of these processes, there is a potential for some of that residual material, or radioactive contamination, to become airborne, posing a risk to communities at large because the material can travel long distances. The current state-of-the-art air monitoring systems, which cost thousands of dollars, are limited in the volumes of air that can be screened in a given time, potentially allowing material to avoid detection. So, at the Savannah River National Laboratory, I'm a part of a team developing a complementary system which can monitor large volumes of air very quickly and cost-effectively. And it's an air purifier and HEPA filter, which for just a couple $100 can screen nearly 100 times the volume of air as the current state-of-the-art systems. Now, how do I use this system to determine that the air is safe to breathe? Well, the filters I use are sprayed with a special material that will emit light in the presence of radioactive contamination. So, I take photos of the filters and use the amount of light I detect to quantify that contamination. Now, there is a slight problem here. These filters emit very little light. So little, in fact, that it's often difficult to distinguish it from the electronic noise of the cameras. This is, coincidentally, a similar issue faced by astronomers who image cosmic objects like galaxies and stellar clusters. To improve the clarity of their photos, they utilize an image processing technique, which minimizes light pollution and maximizes signal. And we can see an example of this in the upper two images here, which are actually the same photograph of the Milky Way galaxy. So I've taken this technique and applied it to an image of an air filter, which screened air from a contaminated environment. And we can see that after processing, the contamination caught on the filter appears clear and bright, just like the stars in the Milky Way. So just how astronomers are utilizing this technique to image cosmic objects, at SRNL, I'm using it to image air filters to help ensure the safety of communities from airborne radioactive contamination.
Thank you, Austin. And so the next time I need to inspect the HEPA filter of my vacuum cleaner, I'll reach for my telescope. Did I understand that right? All right, this concludes the second category of presentations, national security. Now, when many of you think of national labs, they think of large equipment used for scientific discovery. And yes, national lab researchers, including the following 5 finalists, harnessed world-class expertise, facilities, and research programs to deliver fundamental science breakthroughs. Once again, We will be right back after these important messages.
Hi, this is Congressman Nick LaLota. In Congress, I'm proud to represent Brookhaven National Laboratory, one of just 17 national laboratories in our country and a true hub of innovation right here in Suffolk County. Today, I want to wish the best of luck to BNL's own Dr. Preetha Sarkar as she competes in the Department of Energy's National Lab Research SLAM in Washington, D.C. Dr. Sarkar is a dedicated and accomplished researcher and an early career scientist whose work reflects both deep expertise and forward-looking innovation. She represents the bright promise of Brookhaven. Her research is helping bring quantum computing closer to everyday reality by developing more reliable and scalable materials, moving this technology from theory into real-world application. This is exactly the kind of work Congress continues to support, including $125 million in fiscal year 26 funding for quantum research, with BNL playing a key role in keeping America at the forefront of global innovation. It's researchers like Dr. Sarkar who strengthen Suffolk County's reputation as a place where big ideas become real solutions. I know she will make our community proud, and I wish her continued success in this competition and beyond. Thank you, and God bless.
Hi, I'm Congresswoman Delia Catalina Ramirez, and I'm the proud representative of Illinois' mighty 3rd Congressional District, home to Fermilab. I'd like to congratulate Fermilab's own Dr. Bi-Young-Cho Yu on his selection as a National Lab Research SLAM finalist to share the story of his breakthrough science research. Dr. Yu, Illinois 3 will be cheering you on as you compete. Good luck.
Hi, I'm Congressman Bobby Scott of Virginia's 3rd Congressional District, and I'd like to congratulate Dr. Tyler Haig on his selection as a National Lab Research SLAM finalist and wish him the best of luck on his presentation.
Hi there. Congresswoman Latifah Simon here, and I am so proud to represent California's 12th Congressional District, home to Lawrence Berkeley National Laboratory. And today, I am so excited to extend my warm congratulations to Dr. Balaji from Berkeley Lab on his selection as National Lab Research SLAM finalist. My team and I are so proud of all of the incredible work being done at Berkeley Lab. This innovation, this amazing institution, and its genius coming out of California 12, I couldn't be more proud. The world is watching, and I'm so glad that we're a part of the history coming out of this institution. I wish Dr. Balaji the best of luck with this presentation.
Hi, I'm Sam Liccardo, and I serve you in Congress, proudly representing California's 16th District, home to the SLAC National Accelerator Laboratory. I want to congratulate Dr. Jenny Smith on being selected as a finalist in the National Lab Research SLAM. As an engineer at SLAC, Dr. Smith represents the incredible talent and innovation that make our region a leader in science and technology. In her presentation, Dr. Smith is going to explain how her work helps scientists quickly sort through the massive amount of data and capture the most important signals, enabling new discoveries about our universe. Congratulations, Dr. Smith, on this outstanding achievement, and best of luck with your presentation.
When you need a visual aid in a pinch to explain your theory, I bet many of you are reaching for a paper napkin or perhaps the proverbial back of an envelope. Well, our next speaker has got a much better solution. She has, in essence, her PhD thesis tattooed on her arm. And no, you're not going to see it because she's wearing long sleeves, but I really wish I could have been there in the tattoo parlor when they asked her what design she wanted, and she replied, "The electronic band diagram of graphene, please." Ladies and gentlemen, from Brookhaven National Lab, Dr. Preetha Sarkar.
one of the reasons why we haven't yet cured diseases like Parkinson's or Alzheimer's is because to model these complex diseases at a molecular level, today's computers aren't enough. The computer systems we use today, classical systems, encode information in bits, which can have two opposing states, like the two poles of a sphere, north and south. Modeling Alzheimer's with these classical bits would take billions of years. Future quantum computers, however, can do the same calculations in only a few hours. Unlike classical computers' bits, a quantum computer's qubits encode information not just at one position or the other, but anywhere on that sphere, all the possibilities in between. The behavior of these qubits can also be linked to each other, or as we call it, entangled. 20 entangled qubits can store as much information as 136 million classical bits. Quantum computers will have direct applications in medicine, data encryption, and national security. That's a bold claim, given that we haven't yet built a reliable, cost-effective quantum computer. And why is that? Because we need better qubits. Current qubits crosstalk. They degrade and lose information over time. That leads to errors. These qubits also require massive cooling systems, since they work at temperatures that are colder than outer space. One method of building qubits is to use superconductors, materials that conduct electricity without losing any energy. At Brookhaven National Laboratory, my research at the Center for Functional Nanomaterials focuses on building better qubits using high-quality superconductors called transition metal silicides. I build qubits, nano-sized electronic circuits using these silicides. The qubits I'm making will work in an environment that's 10 times warmer than current superconducting qubits, and will require a far less complicated cooling technology that is over 50 times cheaper. They can retain information longer, and we're making them using the same techniques used to make today's computer chips. A quantum revolution is approaching. It can help us cure diseases like Alzheimer's and Parkinson's. It can create opportunities we can't even imagine. But when it arrives, the quality of qubits will determine what results we get, and hence the materials we use to build those qubits with.
Thank you, Preeta. Now, obviously, if you want to talk to her later on, now you have a conversation starter, right? You just say, "May I see your tattoo?" But be specific, because it's not the only one she has, okay? You want to be careful. All right, show of hands. Who in this room has already traveled once or several times in his or her life from Los Angeles to New York? A number of you, okay, so did I. Now, how many of you did that on a bicycle? That's what I thought. Well, our next speaker did when he was an undergrad, alone, and with his tent, which he would pitch in National Park or with permission in people's backyards. What a trip, hey? He saw Yosemite, Las Vegas, Grand Canyon, and Fermilab. From the outside at the time, but for the last 5 years, from the inside. Ladies and gentlemen, from Fermilab National Accelerator Laboratory, soon to be Dr. Byung-Chul Yu.
More than 100 years ago, humanity didn't even know that electron existed. People were curious about the unexplained phenomena, the static in our hair, drifting compass needle, lightning in the sky. Then scientists uncovered the electron. opening a window into the invisible world with new eyes called detectors. At the moment, science ignited the first revolution. Every one of us carries the legacy of the revolution in our pockets, our smartphone. Now, once again, we stand before another unseen world, one beyond our understanding today. We call it dark matter. Dark matter has a mass, so we know it's out there from its gravitational effect that shaped the universe. However, we have never detected it directly. Globally, many different efforts are exploring this hidden world. Among them, one pioneering approach focuses on the muon. Muon is one of the fundamental elementary particles we know best. Fermilab muon G-2 experiment measures how the muon spin behaves inside the magnetic field, and we have reached the highest precision ever achieved in the world. With this world record precision, I'm now using this experiment to search for the entirely new thing, searching for dark matter that may preferentially interact with the muon. If such dark matter exists, it could induce a subtle oscillations in muon's motion. It's a very, very faint signal that's incredibly difficult to detect. It'll be like trying to hear a whisper in the middle of a storm. And my research is the first to search for the whisper. Within the next year, I will open a big chunk of data and scan and explore the dark matter mass ranges at 8 orders of magnitude where dark matter may hide. And each mass point is a chance to listen for the whisper from the cosmos. We once turned on the light and revealed the first invisible particle. Now we seek the next hidden world. Discovering dark matter will push our world into a new era. It will not only change the physics, but also it will reshape how we understand the universe. And with this step, it could spark technological revolution beyond our imagination, affecting how we live and how we connect.
Thank you, Byung-Chu. Can you hear that? Dark matter is whispering to us. All right. Those of you who have kids in college know how hard it can be for these young people to decide what they want to do with their lives. So when the next speaker told me that he started his career in nuclear physics at age 17, I said, "Whoa, you really knew what you wanted to be then, huh?" Except that physics was his backup plan for being a rock star. And he did play with metalcore group Oh Sleeper, but then circumstances dictated otherwise. If you want my opinion, it's their loss and our gain. Ladies and gentlemen, from Thomas Jefferson National Accelerator Facility, Dr. Tyler Haig.
You may recall from school that nuclei are made of protons and neutrons. You may have also learned that these protons and neutrons are made of smaller subatomic particles called quarks. And what you probably didn't learn is that when you take those protons and neutrons and you put them inside of a nucleus, those quarks are fundamentally changed. And we don't know why. If we don't understand the forces that cause this, we cannot understand how you take the basic building blocks of the universe and form the world around us. To study the inside of these nuclei, you have to break them apart. At Jefferson Lab, we do this with an electron beam that's high enough energy it can puncture into the nucleus and scatter directly from a quark. But nature will not give us a clean signal. See, we want electron in, hits quark, electron out. That middle step poses a problem. Who's to say that the electron didn't lose some energy on its path? Who's to say that it didn't hit the quark twice, or hit more than one thing? Right now, we have to use theoretical models to approximate the contributions of these because it's a feature of nature that these will happen, albeit a little less frequently, and are indistinguishable from the main signal. But, though we can't measure them now, with an antimatter beam, we could. Researchers at Thomas Jefferson National Accelerator Facility are developing technology to make our electron accelerator also work as a positron accelerator. Positrons are just the antimatter version of an electron. Now, sci-fi tells us that when matter and antimatter meet, they annihilate in this cataclysmic release of energy. Fortunately, given that there is antimatter all around us and inside of us, this is hyperbole. If every single one of our planned 6 trillion positrons per second were to annihilate, the energy released in a minute of beam time could power a 60-watt light bulb for only 1 second. Now, for our purposes, positrons and electrons are completely identical. They just have opposite charge. And conveniently, these processes that we need to correct for have a feature where they contribute oppositely to your measurement when you flip the charge of the beam. So, some of the least constrained of these in my research are two-photon exchange and Coulomb corrections. You don't need to worry about what they are, they're just different ways of interacting. So, last year, to study this and understand the impact of these on my personal research, I proposed an experiment that will measure these. You can take an electron beam and a positron beam and make the same measurement, and the difference between those two data sets is a direct measurement of these previously unmeasurable processes, improving the precision of both past and future nuclear physics data. And if we find out that our models are wrong, then we may have just upended our understanding of how nuclei are formed. So next time you need to bridge a knowledge gap, consider if antimatter may be the solution.
Thank you, Tyler. Speaking of music, do you remember when Paula Abdul was singing that opposites attract? She was right, of course, but what she did not tell you is that after they attract, opposites annihilate. Another finalist, another rock star. During his PhD, our next speaker played keyboards in a cover band, but when the lead singer was taken ill just before a concert, he stepped in and he sang songs of Red Hot Chili Peppers. How about that? He still plays, and now he even composes. Ladies and gentlemen, from Lawrence Berkeley National Lab, Dr. Yashwan Balaji.
What's the first thing that comes to mind when you hear the words quantum computers? Complicated science? A sci-fi show? It really depends on who you ask. For the government, it's national security. But for my dad, he just wants to know what quantum stocks to invest in. So why all the hype around quantum computers? Some of the world's problems, like drug discovery, encryption, even modeling Alzheimer's, are so complex that the fastest supercomputer would take longer than the age of the universe to solve them. A quantum computer could do it in days or even minutes. That's incredible. But if they're so powerful, why haven't we seen them solve any real-world problems yet? That's because the hardware is still pretty noisy. You see, quantum computers use quantum bits or qubits to perform operations. Our qubits are made using superconducting materials. They have powerful performance, but are unbelievably sensitive to noise. Noise from materials, electronics, environment. But the worst one is something that you never worry about your entire life, unless you're an astronaut. Cosmic rays. Cosmic rays are high-energy particles from outer space that can pass straight through buildings, concrete, even mountains. When they hit a quantum chip, they create shock waves that can destroy the qubit state, and boom, an entire computation can collapse. Okay, what do we do? One option is to bury a quantum computer 1,000 meters underground. Sure, that works, but your commute is going to be worse than in DC. So our team at Berkeley Lab found a better way to shield them by changing the materials our qubits are made from and engineering them with the larger energy barrier. You see, materials in superconducting qubits are nothing fancy. It's aluminum. Aluminum works fine, but it has a small barrier, making them an easy target for cosmic rays. I'm now working on nitride-based materials that can have a barrier up to 10 times larger. And we've made nitride qubits, and we can show that when a cosmic ray strikes, the shock waves aren't large enough to push through such a high barrier, making the qubits far less likely to collapse. Government is investing billions in quantum, and my job is to make them more resilient. So next time when you hear quantum computers, you might want to factor in cosmic rays when investing in your quantum stocks. But don't worry, because I am raising the bar, or should I say, the barrier, to save quantum computers.
Thank you, Yash. And whoa! Did you see that? No, you didn't, but I swear it was a bunch of cosmic rays passing right here. Isn't that creepy, though? They are absolutely everywhere. Now, talking about finding your calling in life, our next speaker got started with electronics in high school by building subwoofers. Boom, boom. Right. Another interface, if you think of it, between music and physics. And her love of powerful basses turned out to be an asset later on in her career when she started researching cryogenic oscillators and amplifiers. Ladies and gentlemen, from SLAC National Accelerator Laboratory, Dr. Jenny Smith.
Have you ever been trying to learn something new and felt like you just couldn't take it all in? It was like drinking from a fire hose. For today's CPUs, modern experimental data looks even worse than a fire hose. Imagine trying to drink from Niagara Falls. Thanks to recent advancements in microelectronics, we've been able to see more, faster than ever before. Think about your iPhone. Just a few years ago, we could barely capture a megapixel, and now you can burst capture 500 times that in a second. At SLAC, we're using these same advancements to image chemical reactions in real time, probe the origins of the universe, and build quantum computers. But like Niagara Falls, all of these projects are generating overwhelming amounts of data. We're talking whole iPhones worth every second, and we're seeing the same problem everywhere: a bandwidth bottleneck. We can't physically get the data into a CPU, and even if we could, most of it is like muddy water, filled with noise. With CPUs drowning under modern data rates, we're locked out of applying our best computational tools, most importantly, AI, to these cutting-edge problems. Without a way to channel this data, experiments that we're working on that could lead to improvements in our health, better our lives, and strengthen our economy are just washing by. That's where my work comes in. As an engineer, I build high-performance electronics that are built to handle Niagara Falls. Using low-level code, I take massive data waterfalls and split them into many parallel streams, where we can filter out the noise extract the meaningful signals, and reduce the overall data rate in real time. At SLAC, our platforms adapt efficiently across experiments, saving DOE resources and broadly accelerating discovery science. This technology has captured the earliest light from the whole universe. At Beamlines, it's enabling real-time feedback so physicists don't miss fundamental discoveries. In the coming decade, the DOE Genesis mission will double scientific productivity, and it's going to do that by connecting large data sets with intelligent analysis. My work provides the critical link between these and will be key to ensuring Genesis mission success. Modern experimental data isn't slowing down, and we shouldn't either. I'm working on the universal link between the experiments we do and the discoveries we make, so that downpours of data are channeled into breakthroughs that better our lives.
Thank you, Jenny. Now, that is the type of photograph that you post on Instagram, right? And then there is the type that you just don't post anywhere, such as the one of my visit to Niagara Falls. All right, this concludes scientific discovery, and if you've listened carefully, you have heard that modern technology often requires advanced materials. And that's precisely the area of our final group of 4 speakers and of many other researchers at the national labs who develop, characterize, and apply these materials. Once again, a word of encouragement.
Hello, I'm Carl Mueller, Director at Ames National Laboratory. The Ames Lab community offers its congratulations to Dr. Emily Lee on her selection as a National Lab Research Slam finalist. Emily truly embodies our Ames Lab values of creativity, community, and collaboration. We wish her the best with her presentation as she explains how she's exploring the nature of catalytic sites and chemical reaction mechanisms for energy security.
Hi, this is Congressman Bill Foster, Congress's PhD physicist, and proud to represent Argonne National Lab as part of the 11th Congressional District of Illinois in the House of Representatives. And wish the best of luck to Dr. Haley Gia, Argonne Slam finalist.
This is Congresswoman Bonnie Watson-Coleman, and I am proud to represent Jersey's 12th Congressional District, home to the Princeton Plasma Physics Lab. I'm cheering on PPPL's own Andrew Powers as he competes in the 3rd National Lab Research Slam. Good luck, Dr. Powers.
Hey everyone, this is Congresswoman Melanie Stansbury, proud to represent New Mexico's 1st Congressional District and home to Sandia National Labs. And I am excited to be here today to cheer on Dr. Samantha Cruz, who is representing Sandia Labs in this year's National Lab Research Slam. Sandia plays a critical role in advancing American innovation, scientific research, and strengthening our national security while tackling some of our biggest challenges facing our communities and our planet. And Dr. Cruz represents the next generation of scientists carrying that mission forward. So Dr. Cruz, all of us here at Team Stansbury are cheering you on and wishing you the best of luck in this competition. You are making us proud.
When you get promoted from postdoc to lab scientist, how do you celebrate the honor and the bigger paycheck? Well, if you are like our next speaker, by buying a new car. But obviously you don't pick the color at random. From her years at the University of Kansas, she still had a blue car, but now that she is at Ames, she needed to buy a red one for Iowa State University. From Ames National Laboratory, Dr. Emily Lee.
As you know, fossil fuels like crude oil
or natural gas are important feedstocks that power our world. They are made of molecules called hydrocarbons, which contain only carbon and hydrogen. Instead of just burning them for heat or fuel, we can directly convert them into valuable chemicals that are used in medicine, plastic, or new materials. The challenge is they are very stable, especially the carbon-hydrogen bond, like a strong lock, cannot be opened easily. To convert them into something new, we need a way to unlock those bonds. That's where catalysts come in. The catalyst is like a helper in chemical reaction. It speeds up the reaction without being used up. The kind of catalysis I'm studying is heterogeneous catalysis, where the catalyst is a solid and the reacting molecules are liquid or gases. The reaction will happen right on the surface of catalyst. Traditionally, the activation of CH bond of hydrocarbon has relied a lot on catalysts containing precious metals, such as palladium or rhodium. They provide high activities, but they are very expensive and limited. Therefore, my research focuses on the next generation catalysts based on the rare earth metals, which are more abundant and more affordable elements with unique properties. These are also critical materials that we know a lot at Ames National Laboratory. To create the efficient rare earth catalysts, I designed a new active structure to help open the bond and also control how the atoms sit on the surface of catalyst. Currently, I'm very excited to observe a good activity for CH bond activation of hydrocarbon with my catalyst, the lanthanum boron hydride confined in zeolite support, which achieving more than 40% yields, suggesting these rare earth catalysts are promising alternatives to the conventional noble metal catalysts for the transformation of hydrocarbons. In short, the heterogeneous catalysis is like a hidden engine behind many of chemical processes that shape our world. And nowadays, we have a way to redesign those engines. By developing new catalysts with more abundant elements, we can make chemical process not only more efficient, but also more accessible for the future, turning simple fossil fuels into valuable chemicals for our daily lives.
Thank you, Emily. You know, the first time I saw this title, I thought that breaking bonds was about home wreckers in love stories or something. My bad, obviously. When you do your PhD at Johns Hopkins, you're not that far from the Appalachians, so you can go skiing frequently until you get a kid. What do you do then? Well, you move to the Chicago area and you swap skiing for ice skating. Our next speaker goes skating every week, if not every day, over lunch break when the kid is in daycare, and I'm sure that does wonders for oxygenating the brain for the rest of the day. Ladies and gentlemen, from Argonne National Laboratory, Dr. Haley Jia.
Has your phone battery ever died at the worst possible moment? Maybe when you are far from home and needed directions. Maybe when you are looking for information you need it right away. It may sound like no big deal, but it actually points to something much bigger. So the same problem that shortens the life of your phone battery can also affect the technologies we rely on every day, from electronics to the energy storage to the power grid. And often, those problems begin with somewhere we cannot see. So deep inside the material, there can be tiny defects. Maybe an atom is missing, maybe it has shifted to a wrong place. Those defects are extremely small, tens of thousands times thinner than a human hair. But even at that scale, they can determine whether a material works beautifully or breaks down too soon. And for a long time, it's been extremely difficult to find those defects, not because we don't have clues, but because the clues are scattered across different forms, different scales, and each one can only tell you part of a story. So what we really need is a scientific detective to help us connect all the clues and figure out what's really happening inside the material. Experts may be able to do that for some materials, but they cannot do it quickly, consistently across all advanced materials. And that is exactly why I built my AI detective at Argonne National Lab. In my work, microscope images are like security footage. Spectroscopy signals are like witness account. Physics-based simulations are like fingerprints of different possible structures. And my AI model allows us to map different data from experiments and simulations, recognize patterns across them, and turn scattered clues into answers. In one of my recent battery studies, identifying those atomic defects used to be almost like a coin flip, about 50-50. But by using AI to combine different clues, I was able to push that to over 90% accuracy. That means we are moving from guessing to knowing, from reacting to problems to stopping them before they begin. Ultimately, my work helps us to get information that we could not reliably access before. So now we can speed up discovery and build technologies that work better and go faster. So next time, if your phone battery fails sooner than it should, remember, the problem starts with somewhere you cannot see. And my job is to make that invisible visible.
Thank you, Ailey. And we are left to wonder whether AI can also spot what others can't see in our secret lives. Now, some people go skiing in the Appalachians, other people go skiing in the Himalayas. Kashmir, to be specific, which features the world's highest ski lift. But that comes with a risk. Our next speaker was told to go skiing that way and not that way to avoid getting shot. Still, enjoying a view of K2 while you are skiing makes it all worthwhile. Ladies and gentlemen, from Princeton Plasma Physics Laboratory, Dr. Tasman Powitz.
Whether you're browsing the internet for cat memes, video calling with loved ones, or checking on your retirement fund, microchips are essential to our modern society. Modern chips are comprised of billions of transistors, each only tens of atoms wide. How can we possibly manufacture such complex electronics at such a tiny scale? The answer is with plasma. Plasma is comprised of charged particles which can be manipulated with electric fields to etch these intricate patterns into silicon wafers. Plasmas are therefore essential to modern microchips, and plasmas are therefore essential to our modern world. But there's a problem. Industry doesn't always understand what's happening within these plasmas used to manufacture microchips. Experimental trial and error has got us a long way, but we're now at a tipping point where this lack of understanding is hindering further progress. My job is to develop plasma simulation capabilities to provide these insights, to help industry develop new plasma equipment to create the next generation of microchips. So, what does this entail? At PPPL, I'm tackling this through 3 approaches. Number one, I map plasma simulations onto high-performance computers. This means faster simulations and therefore quicker scientific insights. Number two, I work to develop algorithms to reduce the cost of plasma simulations, meaning industry can run hundreds or thousands of cases to optimize the design of their plasma equipment. Number three, I process this data with artificial intelligence. This leads to even faster and even cheaper simulations, even allowing for real-time control of plasma equipment. None of this happens in a vacuum, though. A large part of my job is working closely with industry to see these capabilities used to develop that next generation of tools. I'm actually in a unique position where the work that I do directly contributes to improving the tools that I use to conduct that research. That is, I use modern computers to run simulations of plasmas. These help create better plasma manufacturing equipment, which leads to better microchips, faster computers, and even faster simulations. This brings me to what is one of the most important aspects of microchips, enabling future scientific progress. Whether it's plasma simulations, finding cures to cancer, or understanding our place in the cosmos, plasmas are not only essential to our daily lives, but to the future of humanity.
Thank you, Taz. Now, if the accent did not tip you off, then perhaps the middle name did. This researcher is 7th generation Australian. So for sure, he is the great-great-great-great-grandson of criminals. Good thing that crime is not hereditary, right? All right, remember how I announced 5 musicians and we had only 4 so far? So yes, the missing one is our final contestant for this afternoon. She considered a career as a violinist because that was her favorite subject, but eventually she went for her next favorite subject, chemistry. She still plays, and in order to perhaps apply for the Sandia Jazz Orchestra, she is now trying to get back into the swing of it. Ladies and gentlemen, from Sandia National Laboratories, Dr. Samantha Cruz.
I'd like to ask everyone to take a deep breath with me. Did you know that in that single breath, you inhaled microplastics? In fact, in the next 3 minutes of this presentation, you will inhale roughly 150 individual microplastics. In the US, we inhale an average of 68,000 microplastics per day. You've probably seen it on the news. These microplastics are everywhere. Right now, though, you may be wondering, how dangerous are these microplastics to my health? That's a hard question to answer because, unfortunately, these microplastics are typically not pristine polymers. Instead, they've persisted in the environment for months or even years, absorbing harmful pollutants and chemically reacting, increasing their potential toxicity. When humans are exposed to microplastics, they're exposed to all of those additional chemicals, too. To make it even more challenging, in addition to identifying all those chemicals, understanding where chemical compounds are located inside of the microplastic is necessary to estimate how readily those chemicals can be released back into their surroundings, including inside the human body. Unfortunately, the analysis methods currently in use provide either spatial or chemical information, but not both. To understand the limitations of these techniques, you can think of scuba diving. If I asked scuba divers to help me map out different fish in the ocean, and all they could tell me was the color or the shape of the fish at each site, I'd probably misidentify a lot of the chemicals because I'm missing detail. If instead they provided me with a full list of fish species with no location information, I'd have no idea whether these fish were located at the surface or at the bottom of the ocean. Both techniques could be used independently. However, combining them into one technique would increase data quality while saving time and money. And that's where my work at Sandia comes in. In the lab, I use a laser to remove a tiny amount of a single microplastic and analyze its composition. The method I'm developing allows me to vary how far that laser penetrates into the microplastic, providing a 3D image of where different compounds are located. When coupled to a mass spectrometer, this technique also provides a high level of chemical detail. By revealing the composition at varying depths within the microplastic, we can better understand how these chemicals are present inside the microplastic. With this technique, my work will enable scientists to both identify and locate harmful chemicals in microplastics in a faster and more comprehensive way, contributing to a better understanding of the hazards of microplastic exposure. Knowing those hazards enables tactical preparation for any health problems that microplastics may cause, so that hopefully the next time you're trying to relax, you can breathe easy.
Thank you, Sam. And now I propose we all take another deep breath as the members of the jury are retiring to consider their verdict. Good luck with that. And thank you for accepting the challenge of being in the jury today. Let me also invite everyone in the audience, near and far, to please vote now for the People's Choice Award using this QR code or possibly this URL right here. In the meantime, I have the pleasure again this year to be joined by a member of Congress who's been with us for every edition of the National Lab so far, representing New Mexico in the Senate and therefore rooting for both Sandia and Los Alamos, Senator Ben Ray Lujan.
Hello, everybody. It's good to be with you. Thank you very much, sir.
Thank you for being here,
Yes, sir. It's an honor to be with you as well.
I have a few questions for you.
Well, before we get to questions, I'm sorry that all of our judges left because my remarks were all about them. So I will skip past my acknowledgments of the incredible friends that we have who are making an important decision, and I will try not to sway the judges being from New Mexico.
They're gone.
They can hear me. Oh, we can all chatter about that. That's okay to giggle about everybody. Look, the work that each and every one of you do in support of our national labs across America, I just want to say thank you. We're at a very delicate time, not just due to national security responsibilities that we have, looking domestically, not just energy issues. The work that was done, the SLAM participants, the research that they are doing, solving real-world problems that are near-term and long-term. The challenges that we have in looking after how these contracts are put together to bid out to our national labs. I shared with the SLAM participants that I was able to chat with in my office yesterday, that I encourage them to continue to fight and stay at one of our national labs. But I need their help in working with all of our lab directors, with all of the prime contractors, as you work with the Department of Energy, and we look at these contracts, real entrepreneurial leave programs that not just read well, but that work in practice so that all of these scientists, engineers, physicists, mathematicians, they want to stay at the national labs, but we need to empower them to go and to unleash that ingenuity wherever it may be. And I'm telling you, we will get them all back. So I certainly hope that we can voluntarily include real parameters around entrepreneurial leave programs, that we take more from having LD-RD not be a line item protected aspect so we can put real money into this research. Or those of us in Congress will make you do it. So Well, I got one giggle out of that. I appreciate that. But I'm serious about that. And my colleague, Chuck Fleischman, may have a different take on that, being that he is the chair of the Appropriation Committee in this space. But Chuck and I, when we were in the House, we helped to found both the National Labs Caucus and the Cleanup Caucus. And now as a member of the United States Senate, I worked with colleagues across the country, Democrats and Republicans, to be able to create a National Lab Caucus in the Senate, and it is working. So I look forward to learning from each and every one of you. I say congratulations, but to every one of you that participated today, it's absolutely incredible, the application that we see happening on the ground. Thank you for inspiring us, and let's make sure we get them the resources they need and the investment to make this a reality. Thanks for having me, everybody. Yeah.
You have time for another question?
Please.
Yes. You addressed the finalists, but you know, we have many of the National Lab's early career researchers and engineers watching us, either from the room or remotely. And you know, these young people, sooner or later, they will have to show to the members of Congress the value of their work in order to guarantee sustained support for the research. So in terms of communicating with the Congress, what advice would you have for these young people?
Truly, look, well, some have described traveling to Washington, D.C. to visit with a United States senator or a United States representative or a president of the United States, that it can be intimidating. I feel the same way when I talk to you. We're all people. And if you can take a step back and understand that interpersonal dynamics has a place and a role in all of these partnerships, that's an important place to take the first step from. Get to know your members of the United States Senate, the members of the United States House of Representatives, elected leaders. Get to know your lab directors, as challenging as that can be as well, and Tom Mason knows I pick up the phone and I call him as well. But get to know everyone on a personal basis. And the clarity in which you were explaining the complexity of the programs that you have launched and the research, and helping someone like me understand it, if you can help me understand it, you can help anyone understand it. And speaking in that clarity and helping us understand the transformation, not just in our communities where we call home, but our responsibilities across the United States and around the world. Don't forget, we're real people. We're no different. We have to work together to be able to get this done. And being able to convince decision makers about the importance of the research that takes place at our national laboratories, not just for national security, not just in the space now with AI or with quantum, but understanding the economic value and the job creation that should be unleashed from all of our national labs. I really wish there was a chapter built into the work that is being done at the Department of Energy right now, and that we talked about the job creation aspect, the economic engine that our national labs bring every day. And by the way, to my friends at the Department of Homeland Security, any of you out there doing research in this space, tell that directive that they do on their own. They don't do the work like you will be doing at the Department of Energy for work for others. Tell them to come join you. I'll leave it at that so I don't get in trouble with anybody. They know the beef that I have with them right now. But look, be involved, be available, get to know people, invite people for the hike, the jog, the skiing that I heard about. No K2 for me, but interact, get involved. It'll pay dividends when it comes to making investments in our communities and solving the world's problems, yeah.
Thank you, Senator.
Absolutely.
I'm wondering if I can push you a little more on communication, because when these people think of communicating, they think of what we've been doing today, which is communicating to a large group. And I imagine that a one-on-one conversation can sometimes have a major effect into, securing a win for a lab in your case. I'm wondering if you concur with that, and in particular, if you would have an example.
Most certainly.
Please.
Well, first off, I don't know if Chuck, there he is. Chuck Fleischman, everybody.
Hey.
I was going to say some nice things about you, my friend.
Right back at you.
Tennessee's 3rd District, which is home to Oak Ridge National Lab, Congressman Chuck Fleischman.
Thank you. Yeah. My dear friend, former House colleague, now Senator Ben Ray Lujan from the great state of New Mexico, We are good friends. We've worked together on so much over the years, not only our great national labs, but legacy cleanup. And I will tell you all this. I have just left our great Secretary of Energy. I told him I was coming over here. He was before my appropriations subcommittee, Energy and Water, which I chair, but he sends his best, and that's the reason I am slightly delayed. But thank you. It's an honor to be with you both.
Well, since you're here, may I ask you a question that I already asked to Senator Luján?
Absolutely. I hope I answer it almost as well.
Well, I'm going to ask it to you because as he was answering, he said, and I quote, Chuck might have a different opinion about this one.
Okay, and you know, and that's what's great about America. I see a lot of smiling faces out there. Ben Ray and I served together. He's in the Senate now, I'm in the House. But the greatest thing about it is, even when we had differences in the way that we voted and we approached things, we've never had a cross word. We genuinely like each other. And when I see younger people come up here, I think that's so important because that gets lost in so much of what we do, and that's how we can make real progress. He loves his state. His family has a great legacy in New Mexico, and sir, you live up to that. But ask away.
Please. This is about, guess what, early career researchers and engineers. These people, sooner or later, will have to demonstrate the value of the research work they do to members of the Congress, regardless of party. And so we were wondering, what advice would you have from the point of view of communicating to Congress for young early career professionals?
Absolutely. When I was a young man, I had a proclivity for the liberal arts and sciences. I'm a political scientist, I'm a history major, political science major, author, lawyer. I did better with the humanities than I did the sciences. So I went where I was probably meant to be. I am still a strong believer, candidly, in a liberal arts education. I really do. Studied the classics and the like. Having said that, my state, the great state of Tennessee, has made it very easy for men and women who have a great scientific background to pursue that if they have a technical skill. I was the kind of kid that when I was small, I was good with a book, but we had, and this was back in the 70s, I'm 63, we had a situation literally where you'd have somebody who could build something, and the guidance counselors would say, oh, well, we're just going to take them and separate them. Well, guess what? Today, all across America, we need to get people with that great skill set, people who can build things with their hands, who can fix an engine, who can be plumbers, who can be electricians, and we need to make sure that they get the same amount of praise that the kids who were Phi Beta Kappa like me are, because our country needs them. So what I tell young people is, look, if you want to pursue a law degree like I did, that's great. But find something that you like and do it well. Some of the best CEOs I know are philosophy majors, okay? So I'm not saying go out and get your philosophy degree, but the bottom line is let each person develop their potential. I think the real thing is to make sure that with our students in America, whether you're in a rural district, in an inner city district, that they have an opportunity to develop that potential and that skill.
Thank you, Chairman. In fact,
if I could add just one thing.
Yes, please.
Chair Fleischman was saying is, look, Chuck's a Republican. I'm a Democrat. That might surprise a lot of people that we're complimenting one another. Because the bias in this town is that the two parties hate each other. That if you're of one party and I'm of another, we are not supposed to be friends, we're not supposed to talk. Chuck and I are not just colleagues, but we're friends. We can confide in one another, we can conspire with one another. When it comes to our national labs, we do a lot of that. Don't give into this bias that party or another, conservatives, liberal. We need both. We need different schools of thought. We need centrists, we need moderates, we need people coming together. And keep that in mind when you're engaging with members of Congress. Don't give into this notion that they will never speak or work with one another. This is an example where New Mexico, Tennessee, two folks that got elected at the same time that had the national labs in common. We said, let's work together and let's get to know each other. And it's been absolutely incredible.
Find common ground when you can find common ground. And guess what? It's okay if you disagree. That's okay. I just finished a hearing today. The Secretary of Energy was before me, and my friend Marcy Kaptur. You know Marcy well from Ohio. She's a liberal Democrat. I'm a center-right Republican. we never have a cross word. Do we disagree? Sure we do on occasion, but on policy. And I just debriefed with the secretary, and he said, it's amazing how well you all get along. So we try to replicate that. So I appreciate that. And of course, Ben Ray State, New Mexico, is part of our great national park, our Manhattan National Park. It was Oak Ridge, which I represent, Los Alamos, which you represent, and Hanford, Washington. I don't know if we have any people here from Washington State, but there are ways that we can work together. But yes, know your member of Congress, because the reality is, and this is what it is, most in the Senate is different. In the House, most seats are either very red or very blue, okay? There are very few, comparatively speaking, swing seats. There's a few, about 36 to 40, and we respect that. But the reality is, if you're a Republican in a solid blue district, get to know your member of Congress. That's okay. Talk with them, get to know them. Conversely, if you're a Democrat, I just got a call from a Democratic mayor in my district. We talk once a week. He campaigns for me, probably shouldn't do that. I tell him that's against his good judgment, but the reality is, we can work together. Now, does he get frustrated with me? Of course he does on occasion. But that's what's great about our republic. We can have those differences. But and I look out here, I'm seeing some young people. We really want to make that impression so that people get involved in public life like Ben Ray and I did. Because there's a lot of people that say, I would never run for office. I never want to go through that. Well, the reality is we need good people in office.
Right. I have to get running to one more gathering, but I wanted to take the question that you posed to me.
Yes. The question was about one-on-one conversations and whether that can be as effective as talking to a group. Please.
Absolutely. I mean, look, the conversation Chairman Fleischman just had with the Secretary of Energy, few minutes, you're not going to get a lot of time together, but it's going to be memorable, it's going to be significant. I'll take you back a few years. Chuck, you were part of this project. Chips and Science, revolutionary bill to get the United States back on our front foot in this important space. Well, no offense to my friends from NSF that are in the room, but when this bill was being put together, there was no mention of the Department of Energy and the work that was being done at our national labs in quantum and all of these incredible spaces where we know these investments were already taking place and there were gains being made. So me as a Democrat, freshman, new member, I went to Chuck Schumer, who was the majority leader at the time, so he's leadership, and over here, you know, that's everything. I was going to use an analogy that was probably inappropriate based on some of the president's posts recently, so I won't use that one. But I went to Chuck and I said, sir, Department of Energy is not mentioned in this bill. Help me understand why all this work that you're doing and we're going to send this money to the NSF, why is the lab, why are we not included? And Chuck, the way he thinks, sir, he goes, well, not this Chuck, the other one. He says, well, how many votes do you have? And I responded to him by saying, well, this is your piece of legislation, sir. I'm a freshman member of the Senate. I'm not going to go whip against your bill, you know, try to get more votes and things of that nature. And he says, well, go get some votes, and then you come back and talk to me. Well, I called Marsha Blackburn, who's a colleague of ours from Tennessee as well. She's running for governor. By the way, wouldn't he make a great U.S. senator? I'm just saying.
There's your shot.
Marsha, there you go. There's your endorsement. I hope it doesn't hurt you. But Marsha, I went to her and I said, look, DOE's not in here. And she said, well, go talk to a few others. So we went to talk to other colleagues that represent national labs. Well, it turns out that there's a bunch of us. We had a lot of votes. So I was asking Chuck, I think we told him we wanted 18 of the $105 billion. We were not trying to be selfish or greedy, but I went to tell Chuck, I said, there's a lot of support for this, sir. And he says, yeah, well, how many votes do you have? I said, well, we want half the money. And his reaction, what? You wanted 18. And I said, yeah, but you told me to go whip the bill. And I did. And there's a lot of it, so we want half the money. He says, well, I'll tell you what, we'll settle on 18.5. Called Chuck up, said, hey, this is what we got for authorization for the Department of Energy and the CHIPS bill. Can we make it happen? Chuck ran away with it. Language got also included on the House version. But that's how one conversation can change the notion of where investments are going to go, and being empowered to be able to engage with your colleagues, your leadership, whoever it is, and being able to talk to all of your colleagues, because getting those votes, it took one conversation at a time. And over here, no matter how complex things get, do not forget about the importance of simple arithmetic. You need more votes on the other side to get something done. Yeah.
Well said.
Yeah.
Senator.
Everyone, thanks for having me. Yeah.
Thank you so much for participating. Thank you for making time for us.
Oh, an honor, brother. Always an honor. Thanks, everybody. Thanks again, everybody.
Congressman, let me check with the powers that be. Do we have the votes of the...
One more question, or are we good to go? You just tell me.
If you want to say something more, you have to say it fast. Otherwise, the audience is going to kill me for not announcing the winners.
Well, please excuse my tardiness. Congratulations to all the participants, not just the winners. I met with a lot of the young folks who are competing from all the national labs. Thank you to each and every one of you all. We want to encourage everyone to get their expertise and to work towards something, because truly we have great minds and great potential that we're developing. I will say this. I am so privileged to have the job I do. I represent the people of the 3rd District of Tennessee, that is Oak Ridge, which is so, so important to me. Our great national lab, the NNSA facility, Y12 UPF, and something I'm very passionate about, and I hope you are too, legacy cleanup all over the country. Ben Ray does that in New Mexico. I do that in Tennessee. We need it in Savannah River. We need it in Hanford. We need it all over the United States to clean that up. Bottom line, thank you for coming up here to Washington, engaging with your leaders. Please keep inspiring and encouraging the students to keep coming back and doing great things. Thank you.
Thank you. Thank you so much for making the time. Thank you for your support of science and technology. Let me return this microphone and try to find the votes from the jury. I have the People's Choice Awards, but we need the votes from the jury. Microphone. Who's got the votes from the jury? Somebody please bring me the votes from the jury. Do we not have the votes from the jury? Did you turn me into a liar by saying that we had the votes from the jury? Let me informed what is the situation. Apparently, I was getting ahead of myself, so let me put this in my pocket, possibly, or on the side, and do something else, which is, oh, you know, it figures it's when you give up on something that is going to happen. So, goodness, I'm wearing my fitness tracker because I'm doing a lot of steps on the stage today. There we go, perfect. I couldn't take the suspense any longer. So we need to announce that. Every time I'm going to announce a winner, all I do is announcing. I am not going to be delivering the award per se. For that, I'm going to bring on stage the highest ranking lab representative for the corresponding winner. Are we ready? In the category Energy Security, the winner is from the National Laboratory of the Rockies, Kalen Rasmussen. Kalen. And could I have Jeffrey Linger? In the category National Security, Senator Lujan would have been proud. From Los Alamos, Marina Mancuso. At Fitch. In the category Scientific Discovery, from Lawrence Berkeley National Lab, Yashwant Balaji. Next time we'll have to sit in the front. That's going to be easier. And in the category Advanced Materials, I need to take a breath for this one. And Senator Lujan will be sorry he just left. Sandia National Lab, Sam Cruz. We have Tracy Durbin. Tracy, are you somewhere? Oh, you're right there. Get out of your way for the picture. All right, that was the jury, but remember we have another award, which is the People's Choice Award, and I have the outcome of that as well. So in the category People's Choice, I am delighted this year that we are going to give the 5 awards to 5 different people. No one is going to get 2 awards this time. So the People's Choice Award goes to Slack, Jenny Smith. And we have, John is there, just back of you. All right, well, only 5 people will take an award home, but if you ask me, all 17 of the finalists would have deserved an award. They worked so hard on their 3-minute talk. They went through so many iterations and rehearsals. They had to buy a suit in order to speak here in the Congressional Auditorium, and they exposed themselves to, and their research, to the judgment of such a critical audience as yourselves. Could I please have all 17 finalists on stage one more time for a final collective round of applause? Thank you, finalists. You can exit last in, first out. Yes, that means you, Sam. You wouldn't believe what's going on in their mind with a drop of adrenaline at this point. They are unable to think straight. Well, I'm acknowledging the finalists. I would like to acknowledge everybody else who's been supporting this effort. We had people from Congress on stage. We even have people of Congress in the room applauding the finalists. Let me acknowledge Congressman Bobby Scott in the room. Where is he? Over there. Congratulations. Thank you so much for joining us today, for supporting this effort. And he's not the only person that I would like to thank. Obviously, this event would not have been possible without the many sponsors for this event. They are all listed in your programs, and we are very grateful for the support of these organizations. And obviously, the event would also not have been possible without the many staff members of all the national labs who contributed to the organization. They are over there on the side and even behind me supporting this event. Too many for me to name, so let me just focus on the core team. In the middle, the postdoctoral and student programs director from Los Alamos, Antonia Sanders. On her right, which means your left, the communications manager from Lawrence Livermore, Stephanie Terza. And on the other side, the government relations officer from Sandia, Jason Jarvis. Thank you so much for being with us today. See you soon for the next edition of the National Lab Research Slam.